This video is brought to you by a cannon, and this is one of those like firing ones, so get excited. Okay, so now we're going to calculate a standard deviation from another data set. I'm going to use Excel, but then I'll show you how you can copy and paste this into Desmos. So this data set is the number of arrests in the United States for possession of marijuana. Note that these are in thousands, so this is 620,000 arrests in 2008. That's a very common way we don't write all the numbers out, like to make it smaller. And we're going to find the mean and the standard deviation for this. We're also going to include the units. The first thing we need to note here is, why are we finding the sample standard deviation rather than the population standard deviation? And maybe the obvious answer is that there are more years for which there were marijuana arrests than just these years, right? So this is does not include all years that individuals were arrested for marijuana. And there could be arguments that maybe there's a particular reason why we wanted to treat this as a population as opposed to not to, but I think this is pretty clearly just a sample of years for which there were arrests. Okay, so let's go to the calculations. Here's our data set. I left it in the same formatting. We need the mean here. As you recall, hit equals, type in average. Note you can just double click with this function. It sets that out, and we are selecting this row. There is the average number of arrests. We'll give ourselves a few more decimal places, and then the standard deviation. This is sample standard deviation, so we're doing stdev.s, and we're selecting all these values, and there it is. Since these are in the thousands, one of the things we could do is multiply each of these by 1,000, and that gives us the actual values for this. And then if we wanted to do this in Desmos, one of the things we can do is copy this, and I'm not 100% sure this is going to work, and then go over here and paste. Whoops. Can I paste this in here? Oh, I didn't want to do it. I wanted to copy. Control C. It doesn't want to do it in this format. I think we might have to paste it in as a column. So I'm going to transpose this. Let's see what happens when I copy this as a column. There we go. So if you copy it as a column from Excel into Desmos, it will work. I need to label this, and then I can type mean A. Note we got the same thing, and we could do stdev of A, and again we've got the same thing. So two different ways to calculate it, or two different technologies to get to our calculation. So our answers there, let's see, I didn't write them down, my bad, let me write them down, were the mean number of arrests for this time frame was 578,400 arrests, and the standard deviation was approximately 50,509 arrests. Okay, so we're curious about how spread out these data are, and you could see that maybe just from inspection it doesn't look too bad. 50,000 compared to 578,000, like that's not a particularly large number. 50 compared to 500. So we need maybe a better numerical measurement, and that measurement is the relative standard deviation, which we call the coefficient of variation. It's labeled C subscript V, and it's simply the standard deviation divided by the mean. Now notice we've got the symbol for sample standard deviation divided by the sample mean, or population standard deviation divided by the population mean. It might be nice for you to just simplify this for yourself and just say, well, I know whichever way I've done it, if it came from a population, I know the symbols will be population symbols. If it came from a sample, I know we'd be working with sample symbols. So it's just the standard deviation divided by the mean, whatever I got from the data set. So the coefficient of variation for this data set is going to be the 50,509 divided by the 578,400. Now, we typically write this as a decimal place. I'm going to go back to Excel here, and I'm just going to say CV. It's going to be equal to the standard deviation divided by the mean. Bam, there it is. That's my decimal value, 0.0873. We can convert that to a percentage because that is what this is. It's the percent of the mean that is the standard deviation. So 8.73% of the mean is standard deviation. That's not particularly high. So what that's telling us is the data set, like we noted just by looking at the data values, is not that spread out. They're fairly clumped together, which tells us that rests were fairly constant in this time frame. The number of arrests remained relatively the same. So some of the things, some arguments we might make from that are things like, hey, whatever laws are being enacted are not decreasing the number of arrests. So we're not deterring possession of marijuana. Or maybe if we're trying to make a positive spin, we're saying, hey, marijuana is not getting out of control if we feel like these numbers are not huge numbers. Okay, I'm going to skip these next two. I guess I kind of already answered them. And we're going to get to some more kind of conceptual things of what is standard deviation really measuring. This one isn't so helpful. It's just looking at numbers. Let's skip to number 7. We want to know which one do we think is going to have a larger standard deviation, remembering that this is spread or average distance from a center value. So if our first data set is the 40-yard dash times for starting running backs in the National Football League, one thing to note is these guys are paid to run fast. So they're all going to be running pretty close to the same speed, give or take a couple seconds maybe, or a couple milliseconds. Whereas if we take a large class of math students, there might be some students in there that were runners professionally or in high school or currently running on the track team in college. Jackson College doesn't have a track team, but like University of Michigan does, or of that nature. And there are students that are not interested in running at all, so they haven't been training, and so they're not fast. So there's going to be a bunch of different speeds for data set 2. That means data set 2 will have a much higher standard deviation because the speeds are going to be all over the place. Here's another one. Average monthly temperature in Chicago. Summertime, Chicago is nice and warm, 90s, 100 degrees. Wintertime, Chicago's the negative degrees. Average monthly high temperature in Los Angeles, summertime, nice and hot, 100, 110, I'm not quite sure. But in wintertime, it's maybe 70s, maybe 60s. So the highs and lows for Los Angeles are not that far apart, where Chicago is going this huge different bits. So data set 1 will have a much higher spread, a much higher standard deviation. Okay, 2 more questions that get at this. One here, we have a math class that has a mean score of 74%. This is the morning class. And a standard deviation of 3.6%. This is morning class. The afternoon, they have, the same mean score. So I'm going to use an A for afternoon. And their standard deviation, is 19.2%. What this is telling us is in this class, most students, on average, the students are all scoring around a 74%. So most of these students are passing. Some are a little below, some are a little above. There's not too many high performers, maybe not very many 90s, if any. Whereas in this class, we might have a couple 90 or 100% students and maybe a couple 30 or 40% students. So these are really spread out. Maybe it's because it's after lunch and some of the students are sleeping. We're going to skip 10 because we can't record each other's heights. So hopefully you're getting the picture that standard deviation is taking a look at the data values in the data set and saying how far away are they from the mean. If there's lots of outliers in your data set or a few outliers in your data set, that's going to kind of mess with the standard deviation and make it not a very good measurement or a very accurate description, because the mean itself is not a very accurate description of the center. So the two together aren't really describing the data set very well. And in our class, we don't really have a good answer to describe the data set when there's outliers. In 4.7, we're going to be looking at what's called a normal distribution, and that's when there aren't really outliers, and the mean and the standard deviation make a really good description of what's happening in the data set.